Potato starch, otherwise known as amylose, and glycogen-4. What is the function of these molecules in our biochemistry?
Vodka.
Energy, right? We burn these things for energy. We take the sugars from this and we burn them, break them down to get ATP, to get energy. Amylose is about 20% of what makes up the starch molecules that we're talking about coming from food. It has 250 to 4,000 glucose molecules connected by alpha-1,4 glycosidic bonds. So when we talk about starch, we're talking about incredibly massive chains of glucose. Sugar after sugar after sugar after sugar after sugar after sugar after sugar, which is why some of these high starchy foods are also high calorie foods. Because starch is an incredibly dense caloric molecule because of the number of sugar molecules that are found inside of it. We call it a straight chain even though it can coil, and frequently does coil, when we talk about the aqueous solutions where we find it, but it is still a straight chain as opposed to the branch chain that you have for amylopectin. Amylopectin is about 80% of starch. That's the branch chain polysaccharide. Still has the alpha-1,4, but also alpha-1,6 at those branch points, the points where it branches off and moves away. But each one of those branches is still going to continue as a alpha-1,4 straight line, where there could be another 1,6 branching point somewhere in there. And then we have this little thing at the bottom that tells us that it hydrolyzes easily in water and acid to give smaller saccharides, smaller molecules, smaller polysaccharide molecules. Those can further divide down until we eventually get all the way to that base form of glucose. Here's the thing. If you were to take glucose and put it on your tongue, what would it taste like? Not a trick question, it's sugar. What would it taste like? It tastes like sugar. It tastes sweet, right? Anybody ever licked a raw potato before? Does it taste sweet? No. But what's starch made out of? Sugars. Lots and lots and lots of sugars. Here's a little home experiment that you can run if you want. You can go, next time you get a little bit of cracker, I wouldn't suggest with the large cracker because unless you're a really good saliva producer, this is not going to be a fun experiment. But if you take a little bite of a small cracker, like a saltine or otherwise, chew it up really well, get it nice and moist with your saliva, but leave it on your tongue. That's why I don't suggest doing it with a mouthful of crackers because it'll just give you dry mouth from HE double hockey sticks. But leave it on your tongue for a little bit. At first it's going to take salty because it's a saltine. That's what they're named after, right? But after a little while, it won't be salty anymore. It'll just be kind of this blandish thing on your tongue. But give it a little bit more time and eventually it will start to taste sweet. Why? What's happening?
Your mouth is slightly acidic.
Your mouth, well, sort of. More specifically, your mouth has an enzyme. Your saliva has an enzyme that will break the alpha-1,4 glycosidic bonds in starch. It breaks it down, and if you give it enough time, it will break that starch down into smaller and smaller molecules until you eventually get to disaccharides like maltose, and eventually glucose. And we could go back and check. Maltose is not terribly sweet, but glucose is about 75% of sucrose. So once we get down to maltose and sucrose, you start tasting sweet. Anything larger than that, your tongue does not recognize as a sugar, and so it does not taste sweet. But you give your saliva long enough, and it will break down enough of those sugars that you will actually taste them. Glycogen. Polymer of glucose stored in the liver and muscle cells. Your cells hydrolyze these long chains at a rate that's large enough to maintain blood glucose levels between meals. It's very similar to amylopectin here, which is effectively what we call glycogen, but it's even more highly branched. Once again, we're held together by alpha-1,4 and alpha-1,6 glycosidic bonds, and you get them about every 10 to 15 glucose units. So a highly branched, energy-dense molecule. Your liver and your muscles synthesize it, they break it down as they need it. The whole point of activity, like a little bit of aerobic activity, The whole point is to drain your muscles of the energy that they have, of the glucose that they currently have, and force them to start breaking down the glycogen. And if you continue going for a little bit longer than that, you force your liver to start breaking down into that glycogen too, which is what's supposed to help activate your metabolism and keep things moving, burn through your energy stores. Because if you never force your liver to burn through your glycogen, then your body never needs to tap into the long-term energy that it has stored in your fat cells. Which is why you have to do more than 5 minutes worth of exercise to make a significant difference when it comes to an aerobic exercise. You have to burn through the stores in your muscles and burn through the stores in your liver. Because if you only barely touch that, your liver's like, no, it's okay, we got this. You're going to eat in a couple of hours, we're good. And then we get to this guy, cellulose. Cellulose is the major structural component of wood. It is just like starch, amylopectin, and glycogen. It is simply a I shouldn't say simply. Cellulose itself is a polysaccharide. Now, when we actually talk about wood, wood is both cellulose and also proteins that you find that embedded within that makes it even stronger, which is where lignin comes in. We don't really need to talk a lot about that. But the point of this is to appreciate, what do we do with wood?
Burn.
We burn it for fuel, sure. We build our houses out of it. Some of you are actively writing upon it right now. Did you know that the paper that you're taking notes on, the paper that you use to print your notes on, is simply a sheet of sugar? Did you know that that is effectively a structural isomer of the rock candy that you begged your parents for when you were a kid? That maybe you still go, I don't understand why anybody buys rock candy, but like it's a nifty little thing that they color coded or something. But it's just crystallized sugar. It's just sugar cubes in a different shape. But still, it's sugar. And yet wood, which is cellulose plus lignin as a protein, is actually a very strong structural component. Houses made out of wood are sturdy. Wood lasts quite a long time in the right environment. It can also last a very brief time in the wrong environment. What makes wood different? There is another word for cellulose other than just wood. We have a dietary word for cellulose. What do we call cellulose in our diet? We call it fiber. It's important to have fiber in your diet. It helps keep you regular. What does fiber do in your diet? How many calories do we get from fiber? Why is it that celery is considered to be a negative calorie food? Because the energy that it takes to masticate that celery and then to attempt to digest that celery is more than the energy that we get from it. Because celery is pretty much just cellulose and water. A few micronutrients that make it healthy for us. Yay! You can't digest cellulose. In fact, there is not an animal alive that can digest cellulose. Well, what are the termites? You say, good question. The termite's not actually digesting cellulose. It's the protistans in the termite's gut that are digesting cellulose. What about all those herbivores that are eating plants? Yeah, they can't digest cellulose either. If they're a pregastric digestion like cows, then they have bacteria in one of their early stomachs that digest the cellulose for the cow, and then the cow will sometimes take a portion of that, dump it into a later stomach, where all of the plant material that the bacteria have digested can then be absorbed. It also digests a lot of the bacteria. But it keeps a nice culture in that front stomach, so that it just keeps growing. Cows will also throw up their food so that they can chew it to get a little bit more mechanical breakdown of all the cells to give the bacteria easier access to all of it and then re-swallow it. That's what chewing cud is. If you ever see a cow that's not chewing something, suddenly starts chewing, yeah, it just threw up in its mouth a little bit so it could re-chew its dinner and then swallowed it again, just to help things along. That's because plants are an incredibly poor energy source for animals. Pandas poop all the time. Because they eat bamboo, which is bad food to begin with, and they have really short intestines. They're bears effectively. They haven't evolved to have these really long intestines like cows, deer, sheep. So they have to eat a lot of bamboo just to get the amount of energy that they need to survive, because they're not even efficient at getting energy out of bamboo. Because we can't digest cellulose. Why not? What's different about that 1,4-glycosidic bond? It's beta. We have enzymes that can break down alpha 1,4-glycosidic bonds in starches. We even have enzymes that can break down a beta bond in lactose, but what we can't do is break down the beta 1,4-glycosidic bond in cellulose. We can't do it. It's pure freaking sugar! And we can't do anything with it, because of the beta bond that's used to make it. It gives a rigid structure to cell walls in wood and fiber and is more resistant to hydrolysis. Cannot be digested in humans because we can't break that beta 1,4-glycosidic bond. You could change humans to mammals, you could change humans to animals. But as nurses, you're not going to be doing a lot of work with reptiles, so humans is the important one, right? Cellulose, beta 1,4-glycosidic bonds. A beta bond with that oxygen pointing above the ring. This looks a lot like starch because it effectively is exactly the same as starch. What's the only difference? Which direction that hydroxyl was pointing before it was combined into that molecule. If it's up, when it's made in a chain, you get cellulose and we can't digest it. When it's down, you get starch and we can. This is not an accidental thing. The plant isn't making a little bit of cellulose and a little bit of starch and then just deciding where to use it. It's making cellulose where it needs to, and it makes starch as an energy storage molecule. Potatoes don't make massive potato tubers for our benefit. They make it for their benefit, and we just steal them. Well, there's some selective breeding in there. Original potatoes didn't make tubers that size either. But. So, that's carbohydrates, polysaccharides. We good on that? Any questions about chapter 13 before we leap into chapter 14? I'll try and get through 71 slides in 20 minutes less than we would have before. There is the possibility, if we're not even approaching the end by the end of this, we can just call it on 3 chapters for this test. And then this one will just be on the next. So I'm fine with starting this chapter. I'm just letting you know that if we cannot finish it, and there's a lot more left, like last time we had like 9 slides left and everybody voted to just have it on there anyway, I'm cool with that too. We can decide when we get there. Just depends on how quickly we get there. So let's talk about esters, amines, and amides. EPA, or people who work for the EPA, environmental health practitioners, monitor environmental pollutions. A lot of the things that we're worried about when it comes to pollutions are esters, a lot of amides, molecules that have effect on us, on our biology. So, let's talk about carboxylic acids. This is a carbonyl group, the C double bonded to an oxygen, right? If this was a hydrogen right here instead of a hydroxyl group, what would we call that molecule? A molecule that had a terminal carbonyl functional group, what would we call that molecule? I believe this question is pertinent to this test. An aldehyde, perhaps? Something that has a double bond on a terminal carbon, a C double bond O with an H next to it. That is an aldehyde, right? What's a ketone? What's the difference between an aldehyde and a ketone?
Ketone is, the OH is like algae. terminal.
Right, the double O, I should say, not the OH, but yes. The double bonded oxygen isn't terminal, it's in one of the middle ones. So you cannot have a ketone unless you have 3 or more carbons, right? Because anything less than 3, and if you only have 2, both of them are technically on the end, right? So there is no ethyl ketone, but you can have a propyl ketone or a butyl ketone, right? So, a carboxylic acid is very similar to that. We have that ketone or the aldehyde precursor, but instead of having the hydrogen on that terminal carbon, we have a hydroxyl. Now once again, when we're looking at this, because it's going to be important later, we call this carboxylic acid, which means that it is by name at least an acid, and acids are what? When it comes to Lewis acids, acids are proton acceptors or donors? They end up after they have deprotonated. Yes, they end up being negative. So how do we make that molecule negative? Well, we could add some extra electrons. That would make it negative, right? But what's the easiest way to make a molecule negative, especially when we have an oxygen that really loves electrons and a hydrogen that's not good at holding on to it? Right? So the part about this that makes it an acid is the fact that it can, in aqueous solutions, become deprotonated. And this is going to show up on slides, but I just like drawing things before we see them on a slide, right? Remember this double bond O like this C that has 2 oxygens bound to it, that's kind of like a pseudo double bond in both directions. So instead of having a double bond and a single bond, it's kind of like having 2 1.5 bonds. And what that means is that draws that electron potential even further away from that O, and so the hydrogen is even more easily released. So it's easy for this functional group in an aqueous solution to donate that hydrogen. And that is why we call it an acid, because acids are, by definition, hydrogen donors. They donate that hydrogen so that it can react with water to form the hydroxide ion, or excuse me, hydronium ion, the H3O positive ion, which brings us back to that pH and measuring pH, but that was like the last test, so we don't have to worry about that ever again, right? The math, maybe not, but the ideas and concepts, yes. So, here is ethanoic acid, here is propanoic acid, here's benzoic acid. Why is that benzoic acid?
Is it benzene ring?
Because there's a benzene ring there. Now why don't we have the oxygen and the hydroxyl hanging off one of those carbons in the benzene ring?
Take it as red.
Because what?
We take it as red.
Well, because it's not that way?
No, because the symbol assumes that
Oh, no, I don't mean the hydrogens here. I mean, why do these guys have to come off of that carbon? Why couldn't these 2 groups right here be coming off of that carbon right there?
because it's an extraneous carbon to the ring.
Because that carbon right there is involved in partial double bonds with everybody else, right? It can't have 3 other bonds. That would end up with way too many carbons. Each one of these carbons is holding on to 1 hydrogen. That's the only thing that you can replace. So the only way to get a carboxylic acid functional group involved here is to have a carbon outside of the ring, outside of the benzene ring. So this is benzoic acid because it is a benzene and a carboxylic acid. That is propionic acid because it is a propane chain, 1, 2, 3, 3 carbons, right? So propionic acid because it is a 3-carbon chain with a carboxylic acid functional group. Everybody follow? So, here's methane, CH4. When we turn it into an acid, or have a carboxylic acid functional group as part of it, so we have our double bonded O with our OH right next to it, and that becomes methanoic acid. That's for the IUPAC nomenclature at least. Ethane, we take the E off and add oic acid. So here's our 2-carbon chain where the terminal carbon has an oxygen and a hydroxyl, double bonded oxygen and a hydroxyl, right? So it's an aldehyde with a hydroxyl. This is frequently written out, and I believe we will see this eventually, but just not yet, as COOH. So if we have the condensed linear format for these molecules, it's written as COOH. This is 3-methylbutanoic acid. Why isn't it 2-methylbutanoic acid? I mean, that methyl right there, we could start counting here and we'd name it, then it would be 2-methyl, right? Why is it 3-methylbutanoic acid? Why did we start counting from the right instead of from the left? Remember when we were naming aldehydes, when we were naming ketones, when we were naming alcohols? The thing that makes it not just a standard hydrocarbon, that's the thing that gets priority. We call this the number 1 carbon because this is the most basic, the most important aspect of this molecule is the fact that it has a carboxylic acid functional group. So that carbon is number 1. So it's 3-methanoic acid, or 3-methylbutanoic acid, excuse me, because the carbon that's part of the carboxylic acid group is number 1. This guy out here, he just happens to be the one on the left because we drew it that way. So since these molecules can come in either direction and be exactly the same thing, we have to decide which side we start at, right? Well, we start on the side of the thing that's part of the name. If this was just a regular methyl group, CH3, what would you call that? If we got rid of this, and got rid of this, and just made it CH3, what would you call that?
One, three,
2-methylbutane. Yes. Because the longest chain now has 1, 2, 3, 4, or 1, 2, 3, 4. It doesn't really matter, right? And then that means that there's one methyl group hanging off, and since it's the only thing that's there, you would start numbering on the left and call it 2-methylbutane. Because you always give it the lowest functional number as possible, right? But when we turn this final carbon into a carboxylic acid functional group, all of a sudden that means that's the number 1 carbon. That's why it's now 3-methyl butanoic acid instead of 2-methylbutane. This guy over here, can you see why it is 2,3-dichlorobenzene? This is, or 2,3-dichlorobenzoic acid, this is benzoic acid right here, and the carbon that makes it, that it's linked to, 1, 2, 3, the carbon that benzoic acid is linked to, that's what we name it after. Some common names versus IUPAC names. Methanoic acid, because it's 1 carbon. Ethanoic acid, because it's 2 carbons. Propanoic acid, because it's 3 carbons. These first 2 are probably the ones that are going to be the weirdest, because methanoic acid is, the common name for it is just formic acid. Acetic acid you guys have heard of before, right? Where do you find acetic acid? We use it in cooking. What do we call it? It has a very distinct and not so pleasant smell. Vinegar. Acetic acid is vinegar. A vinegar solution, I should say, is a dilute acetic acid solution. You don't want to smell a strong acetic acid solution. When I used to make Tris solutions, or EDTA, or not EDTA, sorry, the solutions that we would use to make our gels with has a lot of electrolytes in it, and so you pH it by adding acetic acid. Well, we would get 6 normal acetic acid. You may not know what that means, but trust me, that means there's a lot of acetic acid in that solution. When you did that, you had to open it and pour it fast, because if you opened that jar, it was a 2-liter jar, if you opened that jar and left it there for more than 5 minutes, the people in the hallway would start coming in going, "What is that smell?" Strong. And if you put your nose right above it, it would burn off your nose hairs.
Is that for electric greases?
Yes, for gel electrophoresis, yeah. What are some common carboxylic acids? Ants. They use formic acid as part of their sting when they bite you. Fun stuff. Question?
My roommate went into serotonin syndrome last night, and he was experiencing formication.
Okay.
It's the paresthesia of thinking you have insects crawling under your skins.
Lovely. That's not an experience I would envy. Sour taste of vinegar, we already mentioned that. Acetic acid. What's this called? So, first thing, is it cyclic?
Nope.
No. Second thing, is there anything special about it? Well, we're in the chapter subject where we're talking about carboxylic acid. So, you can expect that to be there. So, where's the carboxylic acid? On one part. That carbon right there, right? With the double bonded O and the OH. So, next. So, you know it's carboxylic acid. So, what's the longest chain? Well, it's got to contain that because that's part of the name, right? So, let's start there. If we go 1, 2, 3, that's one way, or 1, 2, 3, 4, 5. So, the longest chain has 5, right? Which means our first thing that we have is pentanoic acid. We take pentane, right, and turn it into pentanoic acid. Is there anything else? Are we done? We need to describe this as well. Which carbon is that methyl group attached to?
2.
The second one, because here's 1 and here's 2, right? So, we need to add what? 2-methyl pentanoic acid. Once again, is it cyclic? Where's the thing that makes it important? It's obvious here because we're in the middle of the carboxylic acid section, right? But it might not be so obvious if you're given a structure and asked to name it, or perhaps more appropriately given a structure and asked to pick the correct name out of 4 or 5 options. Right? Because I've gotten fairly good at drawing structures in ChemDraw. Just saying. Saving them as images to be imported into test questions. Some of the more complex ones I figured out, I had a brain fart and it was just like, I could just save them right out of the Word document. Just like right-click a picture, right-click save as. The problem is a lot of these things are put together as tiny pictures. So they built them as multiple images of CH3 or CH2 connected together, and I can't just right-click and save that, and I'm not rebuilding it, so it's easier to draw it inside of a knockoff free version of ChemDraw than to try and rebuild that picture in your thing. So you guys didn't know that.
Zoom in as close as you can get. Alt print screen. Start, run, MS Paint, paste, crop it, save it as a PNG. There you go.
No, I think mine was still faster.
One of these.
Because I just like draw 4 things, save as, type in a name, done. This would take a little bit more than 4 things.
You
But
can also grab all those, probably group them, and then save as.
I don't think so. Inside the ChemDraw thing, you're right, yes, but that's what I do. Alright, let's talk about the properties of carboxylic acid. We use carboxylic acid salts a lot as preservatives and flavor. So here's a list of some of those. Sodium propionate. Tell me what that comes from. Before we get to the slides that tell you how, sodium propionate. It's a sodium salt of a carboxylic acid. How do I know? Well, because I know what's coming up. Because I recognize the name. Because that's a section that we're in. So tell me what carboxylic acid was used to make sodium propionate? Name it. you a hint. It's going to rhyme with oic acid. Propanoic acid. See, this isn't hard.
So I'm off this side of the room. Let's hear from it. Except you.
Yeah, except you. You shut up.
I want to see on the exam, the fill in the blank with that.
Rhymes with.
Yeah, we just start talking about that.
Well, I feel for you. When I was in my first getting my master's degree, I was forced to take a biochemistry course, and the undergraduate students got mad at me because the teacher would ask a question. This is a class with 50 students in it. The teacher would ask a question, and not to infer anything about you guys, but the teacher would ask a question, and similar to what I'm currently experiencing, nobody would really answer. And so I am also an instructor, and was an instructor at the time while I was being forced to take this course. And so I appreciated the fact that when an instructor asks a question, it's not for their own benefit, it's for the opportunity for class involvement. And so when it got to the awkwardness of silence, because she sometimes would do that thing where she's just like, I'm not going to give you the answer. I'm going to stand here and wait for somebody to say something. Except nobody would. And so I just got into the habit of just giving her the answer, because I'm getting my master's degree. This is biochemistry. It's what I do. I don't know why I have to take this course, but I have to actually take the course. So I'm sitting in the classroom. And at one point, about halfway through, one student turned around and looked at me and said, "Would you just shut up?" Like,
And I've been trying to talk less.
no. Well, yeah, exactly. That was I was like, my response was, how about you give her the answer then?
That's what we have for.
No, I'm trying to shut up. It's a challenge.
I'm just saying I feel your pain. All right, here's the thing. Carboxylic acids are polar molecules. They have not just one, but two. In fact, how should we know? How do you already know, beyond the fact that it's already drawn up here with our partial charges and dipoles already listed, how would you know, why would you have reason to suspect that carboxylic acid would be polar? Well, there's the hydrogen here attached to an oxygen, right? In other words, if we got rid of that double bonded oxygen, what would you call this right here? That would be an alcohol, right? Alcohols are just a little bit polar. They are at least a short chain one soluble in water because of it, right? If we got rid of the hydroxyl, what would this be instead? It's the same question I asked you earlier.
That
Propanoic acid, okay, not the immediate question I just asked you, but earlier, if we got rid of that, here, let me just draw it. If we turn this into a hydrogen and got rid of this guy right here, what would that be? That would be an aldehyde, right? Are aldehydes polar? Yes. Are they soluble in water because of that polarity? Yes, up to a certain point, right? And more so than alcohols, right? Because that double bonded carbon, that's an even more polar bond than the hydroxyl bond right here, right? That OH bond. So if we know that the OH bond is a little bit polar, if we know that the carbonyl functional group is even more polar, then wouldn't you expect that if we have both of them, that we would get something even more polar? No, of course not. No, that would not be logical.
Negative.
And 4 left terms means no change. Is it 4 left turns mean no change? 1, 2, 3, 4. Yes, 4 left turns means no change. 3 left turns makes a right. 1 block behind you. But that's... Anyway. So, here we have our partial negative charge around that oxygen, because once again, oxygen really likes to hold on to its electrons, right? It's very electronegative, because it's over in the upper right corner of the periodic table, and we remember from our trends in the periodic table chapter way back when that electronegativity gets higher as we move to the right and up, right? Flushed that one a long time ago, right? So, we have our double bond here with our partial negative and partial positive. We have our hydroxyl bond there with our partial positive on the hydrogen, partial negative on the oxygen. Pretty much oxygen likes to be negative. kind of way to look at it. So because of those two partial charges, those two groups of partial charges, I should say, in our carboxylic acid, it means that water can associate in multiple ways with that hydrocarbon. Now remember, normally hydrocarbons that are nothing but pure hydrogen and carbon, those don't get along with water because they have no polar groups to hydrogen bond with water. Even these guys, up to a point, can't get along with water, right? Like when they're small like this, they're going to get along fine. But alcohols only were soluble in water if they were fairly short, right? Even aldehydes and ketones, those guys got along with water, but at a certain point you get too long and they didn't get along anymore. There's too much that water doesn't like and not enough that it does. So do you think that we're going to see a similar pattern here? Yep. It's a lovely table that gives you information, but what we have here is a carboxylic acid. 1 carbon is soluble, 2 soluble, 3 soluble, 4 soluble, 5 soluble, 6 and 7, well 6 and plus 1, 7 as a ring, slightly soluble. Our alcohols hit insolubility, I believe, at 5. Our ketones and aldehydes hit insolubility at 6. These guys are hitting slightly soluble at 6 and 7. Go beyond that, we're going to start having problems. Well, actually, we're already having problems, right? At 6 and 7, slightly soluble. The point is there's just too much non-polar hanging off the end. At some point, you overcome the positive interactions here, and you get to where water just wants to exclude you. All right, we call them acids. So what type of acids are they? The answer to that is weak acids. All acids are hydrogen donors, right? That's what we call them. That's what we mean when we call them an acid. But remember, there were two categories of acids. There were strong acids and weak acids. Weak acids, what makes them weak? Okay, let me rephrase. Why do we call a weak acid? Because it doesn't do what that strong acids do. Very good. It does not completely disassociate. Strong acids completely break up, right? You put them in water, everything dissolves. Everything breaks up into ions. Weak acids, only some of them do, right? So carboxylic acids are weak acids. They do ionize in water. When they do so, they create carboxylate ions. In this case, ethanoic acid creates the ethanoate ion. So propionic acid would make the propanoate ion. And then, of course, we have the hydronium ion over here because of the additional water, or excuse me, the additional hydrogen ion that is given away by that guy right there. That guy jumps over to those guys, and we get an ion and an ion. Since we can make these guys in water, it means we can also make salts out of these guys. So remember when we were talking about ionic compounds and we were talking about sodium nitrate or sodium phosphate, things like that? It's like, well, here's a polyatomic ion, PO4. Here's a polyatomic ion as well. Except now we're talking about polyatomic ions that can get rather large. If we take a carboxylic acid and dissolve it in water, then it will create the ion of that carboxylic acid. If we then add a base like sodium hydroxide or potassium hydroxide, we can neutralize that acid by creating a salt, sodium methanoate or sodium formate. That salt can be precipitated. That salt can therefore be stored. This is why a lot of the drugs that you take the chemical format of the drugs, the way that you get that drug as a powder in a jar, the dried version of that drug, is quite frequently a salt. Potassium benzoate. Anybody heard of that before? Aside from the fact that it was on that slide at the beginning of this section. Preservative in foods. This is benzoic acid. Potassium benzoate is a salt of that. We take the ic acid part and replace it with ate. Potassium benzoate. Why do we call it potassium benzoate, not benzoate potassium? Once again, this is going all the way back to that ionic bonds chapter, the ionic reactions chapter. What comes first when we're naming a salt? The metal, right? So potassium is the metal in this salt, and benzoate is the second part of the name. Benzoate comes second. These salts are ionic compounds. The salts are solid at room temperatures and therefore have relatively high melting points, but are also, by definition, very soluble in water. Or I should say, usually by definition, soluble in water, because salts are soluble in water. They are ionic and interact with the hydrogen bonding of water in order to dissolve. Sodium propionate, sodium benzoate. How many of you guys have heard of monosodium glutamate? Perhaps I should use the more common name, MSG. Heard of that one before? That's MSG. Why is it monosodium glutamate?
Well, it's because there's only one sodium here. There's just one sodium, so that's why it's called monosodium glutamate, because there's only one of them.
Here's the thing, this is glutamate, or glutamic acid. What do you notice over here? What's that? Carboxylic acid functional group. Glutamic acid has two carboxylic acid functional groups. So monosodium glutamate is telling you that it is a glutamate ion that has lost only one hydrogen. Only one of those carboxylic acid functional groups has donated its hydrogen, forming a salt. The other one stays whole and is therefore stable. Does this imply that you could find a disodium glutamate? It implies that it could exist, yes. The conditions that would also deprotonate that salt, that guy right there, would be somewhat excessive to find. But they do exist. But if you ever wondered what MSG was, now you know. We use them as preservatives or flavor enhancers. Sodium propionate, cheeses and breads. Sodium benzoate, that inhibits mold and bacterial growth. So you'll find that for like fruit juices, salads. Monosodium glutamate, stereotypically you find in certain types of ethnic foods, or anything else that you might cook in your kitchen if you like the flavor. Sometimes it gives people headaches though, if you're MSG sensitive, which is why you go places and they might actually advertise that that fruit is MSG free. Links to health. We use carboxylic acids a lot in our biochemistry. And I don't mean just in terms of making preservatives or flavor enhancers. I mean the everyday chemistry that your cells go through in order to survive. Glycolysis is the initial breakdown of sugar. We take glucose and we break it down into two molecules of pyruvic acid. CH3OO and then C double bond O, and OH. This is pyruvic acid. That's the acid functional group right there. That's C double bond and OOH. There is also a carbonyl functional group right there. That's lovely. But here's the thing. That is 1/2 of sugar. If you take glucose, the very first act of turning glucose into energy is glycolysis. That cuts that sugar in half, if you will, and creates pyruvic acid. 2 3-carbon acids. In the presence of oxygen, that pyruvic acid then goes into your mitochondria and goes through the citric acid cycle, otherwise known as the Krebs cycle, which we're going to keep talking about here in a minute, but not to any great length of detail. But it continues to burn it down to create CO2, H2O, and a crap ton of ATP, eventually. But glycolysis is the first step, and it does not require oxygen. But if there is not oxygen around, then your cells will go through a different process of energy metabolism. Instead of aerobic metabolism, it goes through anaerobic metabolism, thus the lack of oxygen as the description there. And that process is called, anybody remember? We named it a while ago when we talked about bacteria doing it. Fermentation, exactly. In bacteria and yeast, when they do it, fermentation results in ethanol, right? But in us, fermentation results in lactic acid. Now, before we move on, because I think this is important to understand just a little bit deeper, they imply it in this slide, this is reduction. We are reducing the amount of carbon-oxygen bonds when we go through reduction, right? Because oxidation is increasing the amount of carbon-oxygen bonds. So what's happening in reduction is we are going from this carbonyl functional group, we're reducing the number of CO bonds from 2 right here down to just 1. But here's the thing. Reduction. Is that the addition of energy or is that the subtraction of energy? Do you remember when we talked about which things? When you oxidize something, the product of that oxidation, the thing that was oxidized, has more or less energy. Less. When we oxidize things, what are we doing? We are adding carbon-oxygen bonds, right? Well, if you keep adding oxygen to carbon, eventually you're going to reach what? What's carbon with all 4 bonds bonded to oxygen? CO2. Right? That's the low energy molecule. That's the thing you're breathing out. So oxidizing a molecule means it has less energy. Why would we be spending energy to make lactic acid? The answer isn't found on this slide because the answer requires an understanding of why we would be doing this in the first place. Glycolysis, that guy right there, it requires a certain molecule called NAD in order to function. It takes a little bit of the energy that is gained from breaking glucose in half. But if there is no oxygen around, then you will run out of NAD. Normally that NAD goes into the mitochondria and it's used to just further burn the sugars. So it's burned from NAD, when it gets energy it's turned into NADH. And then it'll go into the mitochondria, donate that hydrogen and the electron, become NAD again, and then it can go back out into the cell so it can be used for more glycolysis. But in the absence of oxygen, that can't happen. But glycolysis is the only way to get energy. So the reason that this happens in your cells when you are under anaerobic conditions is because it's the only way to keep doing glycolysis. Glycolysis is not a good source of energy, but if it's the only guy on the block, it's the only thing you can do. And so we'll take that NADH and we'll spend the energy in it to reduce pyruvic acid into lactic acid. And while the lactic acid is around, it will damage your cells. But the nifty thing about this, bacteria can't take ethanol and convert it back. We can take lactic acid, and when we get more oxygen around, when oxygen is supplied back to our cells, guess what we can do? We can do this in the opposite direction. We can take the lactic acid, convert it back into pyruvic acid, and then give it to the mitochondria to burn. What do you call that? Anybody in here a long-distance runner? what do you call that when you slow down just a little bit? You're starting to get tired, you're starting to feel the burn, but you slow down just a little bit, and then all of a sudden you get your
Second wind.
second wind. That is when you finally get oxygen back to your cells so that they can spend that oxygen debt to convert some of that lactic acid back to pyruvic acid and start using it again. And suddenly you're not quite so tired. Theoretically, if you're trying to do aerobic exercise, if you're feeling the burn in the middle of the exercise, you're doing it wrong. Because if you're doing aerobic exercise correctly, you shouldn't be creating lactic acid. The whole point of aerobic exercise is to keep oxygen to your muscles all the time. And that's not to say that if you don't feel the burn, like, it's not to say that feeling the burn is a bad thing. Me personally, like when I do a little bit of exercise, which I don't do frequently, I like feeling the burn because it makes me, the next day at least, it makes me feel like I actually did something. Maybe I'm just a little bit of a masochist. I like to punish myself with muscle pain. During strenuous exercise, when oxygen levels are low, anaerobic, pyruvic acid is reduced to lactic acid or the lactate ion. See, all the stuff I was just telling you, except in words on the slide, which makes it so much more important, right? All right, so the citric acid cycle, not just for oranges. The citric acid cycle, otherwise known as the Krebs cycle. This is when we take di- and tricarboxylic acid and we oxidize them and decarboxylate them in order to make a lot of energy. This is what's happening during aerobic respiration in your mitochondria. We are taking those 3-carbon sugars and we are slowly oxidizing them, and every time we do that, it is reducing something else in your cells, and those are the high energy molecules that we can use to make ATP. But we just keep oxidizing, keep oxidizing, keep oxidizing. Eventually we pop off the CO2. And in some of those steps, intermittent steps, we can capture the energy that is being released by the oxidation of those carbons. So here we have citric acid. The start of the citric acid cycle, we create citric acid, we recreate citric acid, and that is oxidized into a 5-carbon alpha ketogluteric acid. So here we go, here's this guy here, and we oxidize it down into this guy right here. What happened? That carboxylic acid group right there, and that oxygen right there, or that hydroxyl pop off, and we're left with just CH2. But we remove CO2, so we have turned the 1, 2, 3, 4, 5, 6 carbon sugar, citric acid, into a 5-carbon sugar. And there's a CO2. There's the first CO2 that comes off from the burning of sugars. We continue through the citric acid cycle, and that guy right there, we break off another CO2 to leave us with succinic acid. That then gets oxidized to fumaric acid. That then gets oxidized to malic acid. That then gets oxidized, or converted to malic acid. That then gets oxidized to oxaloacetic acid. And then we're going to pop up another guy. On the next step, we're just going to keep going, converting our sugars, converting our carboxylic acids to the next guy, to another form, then to another form, oxidizing that form, converting it to another form. Each one of these changes takes an enzyme. It is a cycle because it keeps rolling over and over and over again. We're going to break this guy down, popping off CO2 every time. And then when we get to the end of that cycle, we're going to take a molecule that's left, and we're going to go back and add it to one of those pyruvates that we spent in before, and then that will recreate citric acid, which then starts the whole process over again. This is how you burn food in your mitochondria. We are taking these carboxylic acids, oxidizing them and converting them, and then oxidizing them and converting them, and oxidizing them and converting them. But the point is that there are enzymes that are doing it, and every time the sugar is oxidized, or the carboxylic acid is oxidized, we are reducing something else. something else is gaining the energy that is lost in the oxidation of these acids. And it just keeps going. All right. That's the shortest discussion of the Krebs cycle I've ever had. Oh well. So, let's move on and talk about esters. What's that?
I said, I don't know what you're disappointed in, like the book, the way they summed it up, the fact that you just couldn't go deeper.
Yeah, pretty much that. It's like there's so much that we're just gonna skip over all this. We're gonna gloss over that. We're gonna just like really oversimplify this, and then we're just gonna say done.
Oversimplification.
I understand the point because as much as I'm complaining about that being the simplest discussion of the Krebs cycle, 99% of the people who have to go deeper than that into the Krebs cycle, it doesn't matter. It's like, when are you going to use that? Unless you study the biochemistry of the Krebs cycle, when are you going to use that? I mean, the only time this is ever going to come up as a nurse, maybe, is if you actually look into what a drug does and you find out, oh, it inhibits the fourth step of the Krebs cycle, and you can go, oh, I know what that is. But you might have already known that from like your freshman biology or high school biology, because the Krebs cycle is the thing that the mitochondria do that makes energy. Like, it's one of those things where there's the minimum knowledge, and then there's complete knowledge, and for most people, anything between those two things is not so much worth it, because it's just not going to affect your life very much, unless that's the thing that you do. So, you know, like I complained about how that's such a simple thing to describe, but I also understand that, you know.
It's easy, David.
Yeah. All right, let's talk about esters. Salicin from willow tree bark and leaves, the natural form of aspirin. You absorb that and your body converts it to salicylic acid. Think about salicylic acid, that irritates the stomach lining. Decreases production of the mucus that protects your stomach. But we can make an ester of that, acetylsalicylic acid, and that's less irritating but still just as effective in paper. So what's an ester? And why are we talking about them immediately after discussing carboxylic acids? Oh, good questions. This is carboxylic acid, and this is an ester. What's the difference? What have we done to make this ester? We took this carboxylic acid, ethanoic acid, and we replaced the hydroxyl functional group with a ether bond and a methyl group. But this isn't an ether, why not? What would I have to do to make this an ether? Methyl or ethyl methyl ether. What would I have to do to make this ethyl methyl ether?
Take it with a double bonded oxygen.
Yeah, take it with a double bonded oxygen. What's an ether? An ether, remember when we talked about ethers way back in chapter 11? An ether was just an oxygen in the middle of a carbon chain, right? An oxygen single bound to two different carbons. And we named it by describing it as the two different alkyl groups on either side in alphabetical order, right? Which is why it's ethyl methyl, not methyl ethyl, because E comes before N. Right? But this is an ester, not an ether. So why is it an ester? What makes it an ester? Not just that oxygen between two carbons, but the fact that it's an oxygen between two carbons and one of them has a double bonded oxygen attached to it as well. That is what makes it an ester. So this is methyl ethanoate. Can you see where the nomenclature comes in? It is an ester. So it's going to be an OH, which we're going to see here in a second. But we name it as the thing that was the carboxylic acid. And then we describe the thing that's attached on the other side of that oxygen. Once again, because in order to make the ester, we have to have that carboxylic acid in the first place. So the carboxylic acid is more important than the other thing that's attached to it. Even if the carboxylic acid is shorter. This could be butyl ethanoate. And the thing hanging off the end could actually have more carbons on it. But it doesn't matter. Because the ester bond is what's important. And the ester bond came from the carboxylic acid, which was on the ethyl part. In this particular case. So, how do we get esters? We can make them but through a process called esterification. We do that by combining a carboxylic acid with an alcohol. So in other words, if you add a carboxylic acid functional group to an alcohol functional group in the presence of hydrogen ions and heat, which, once again, to recall previous chapters that are not going to be on this test, but what type of solution would you be able to do this reaction in? It tells you on the slide if you bothered to read it, but do you know it before you read it? What type of solution are you going to find in excess of hydrogen ions? What would you call a solution that has an excess of hydrogen ions? Acidic. Acid catalyst. Hydrogen ions being released by acids, right? Now remember, this is ethanoic acid, so any solution that doesn't have something else forcing it that you added a crap load of this carboxylic acid to is probably going to be at least mildly acidic, right? Because what's ethanoic acid going to do in water? Some of it at least is going to donate hydrogen ions. Mix that with an alcohol and add some heat. Here's the thing. How many arrows do we have here? Not one, but two, which tells you that this reaction is reversible. So esterification is the process of making an ester. Obviously, we can break that down again, which we will discuss in a little bit. So, what's happening here? What do you see right there?
The components of water.
I see the components of water. I see a water molecule, HOH, right? So if you can pop that water off, and then that thing on, you get that. You get the ethanoate part right here, the remnants of the ethanoic acid, and then you get the methyl part right here that comes from the methanol. So, esterification is a process that generates water. Here's an example. Here we have ethanoic acid, once again a 2-carbon carboxylic acid group. We're going to combine it with 1 propanol. That's going to pop off a water right there at the end, and we're going to get ethanoate, but now it's going to be with a propyl attachment to it, so we have propyl ethanoate. Even though this 3-carbon chain is longer than that 2-carbon chain, we still call it ethanoate because it was ethanoic acid that we started with. The OH part is always going to be the acid. Here, it is now color-coded for you. Carboxylic acid becomes the carboxylate. The ethanoic acid becomes the ethanoate. And the part from the alcohol becomes the alkyl substituent. it becomes the thing that comes before the O8. So whatever the acid is, that's the O8. So if it's butyric acid, then it becomes butyroate. And then whatever the other thing is that was donated before. The first word is the alcohol. The second word is the acid. The acid is the main part of the word. They have IUPAC and common names, so ethyl ethanoate or ethyl acetate, because acetate was the name for the ethanoate, right? The ethanoic acid. The 2-carbon acid is just acetate, right? Or acetic acid, acetyl acid. Ethyl acetate, methylpropionate, ethyl benzoate down here, because it's a 2-carbon chain added to benzoic acid, right? So, does everyone feel confident that they could name an ester? Maybe. Confident that you can find the part of the chapter where it tells you how to name an ester? Yeah? Okay. When we're naming an ester, and we're going to come back to it because we're going to talk about going the opposite direction of esterification, of hydrolyzing an ester. When you're naming an ester, the O8 part is always the thing that comes from the ic acid part. All right. Salicylic acid from the willow tree. 1899. They produced this ester from salicylic acid and acetic acid. It made it less irritating to the stomach. They called it acetylsalicylic acid, otherwise known as aspirin. See, here we have salicylic acid. We've got our lovely benzene ring right there. We're combining it with acetic acid. So there's our carboxylic acid. So where's the water? Would you be able to circle it? Look at this reaction on the left and mentally circle the water that's going to be popping off over here. Do you have it? Do you think you know where it comes from? There it is. Is that what you circled in your head? Sure. You didn't make me write it down, so I'm just going to take credit. Salicylic acid. Combining there. In this case, actually, the ester they have there. Acetic acid here and there. Forgive me. That's the reaction they have there. Right? Because we're not reacting with that, we're reacting with this. We're taking the hydroxyl alcohol and reacting with this carboxylic acid group. Sorry?
And the reason why is because it's...
Well, yes. Okay. So here's why I made the mistake. When I looked at this, I was looking at the wrong things. So, and also because I wasn't looking directly at this enough. But I looked at this and saw an alcohol group. Is this an alcohol group right here? It's a hydroxyl, yes. But what is it actually attached to? That's a carboxylic acid group. Which, yes, does have a hydroxyl, but remember, there is a difference between a COH bond and a COH bond.
Oh, okay.
That double bond, but remember what I described before? That double bond actually kind of works like this. So this is just a hydroxyl, yes. But that is not the same thing as this. That oxygen is more strongly bound to that carbon here, because of that shared nature of that bond, than that oxygen is to that carbon. So yes, it is a hydroxyl group in both cases, but it is different functionally because the strength of the bond is different. And so it's not going to be that as the alcohol reacting with our salicylic acid over here, because that is a carboxylic acid functional group. Which is in the same way, I made the assumption that that right there was going to be our carboxylic acid group, right? Because there it is. There's COOH right there, right? So where's the carbon to a single bonded oxygen to another hydrogen? It's right there. That's the alcohol functional group. Combining with that carboxylic acid group. Which is why we end up with our carboxylic acid group intact up here, and then this right here, that's our ester bond. Everybody follow? Now that specific reaction is not going to be that terribly important, but understanding what that reaction is, if that made sense to you, then that means that you're getting a fairly good grasp of this topic. If you are completely lost, then perhaps you are not. But that's okay, because we have more to talk about. Oil of wintergreen. Methyl salicylate. Pungent, minty odor, and flavor. We use it in skin ointments. It can actually pass through the skin. You make that by, once again, combining salicylic acid with a methyl alcohol. And in this case, what's happening? We are now combining a carboxylic acid with a methyl alcohol. So before, we were combining an acid right here with another acid, but that acid happened to have a hydroxyl group hanging off. Here we have a methyl alcohol. So what's going to react with that methyl alcohol? Now that's going to react with that carboxylic acid functional group. Which is why we now have our ester bond right here. Even though we use salicylic acid in both cases. This reaction here, the Bayer company did in test tubes. Because salicylic acid is something that you can find in oak bark and leaves. Not oak. Willow bark and leaves. Right? Willow? Aspen. Aspen bark and leaves. Did it say willow? Yeah. Okay. Right. Salicylic acid. Same thing. But now we combine it with methyl alcohol and we get oil of wintergreen. We can make this alright? Name that ester. First off, where's the ester functional group? Or I should say, what makes this special? The fact that it's an ester, right? Once again, that's easy because we're in the section of the chapter that's all about esters, but on an exam, that's not going to be the case. So you'll need to be able to look at this and go, oh, that's an ester. How do you know it's an ester?
Double bonded oxygen with a single bonded oxygen.
Right. A double bonded oxygen with a single bonded oxygen next to it. Or an ether bond, because that might be the first thing that you see, with a double bonded oxygen right next to it. Right? Now, which side, this is not critical for the naming, actually in this case it is, but in all cases it is, but in this case it doesn't much matter because we have two carbons on both sides. Which side of that ester was the acid? And which side was the alcohol? Because we could flip this, right? We could flip this around. But it'd be the same molecule. But if we keep it drawn like this, which side was the acid? The left. How do I know that? Where's the carbon with 3 bonds to oxygen?
Right. Of that.
Right there. That's the end of the molecule that was the acid. So how many carbons are in this acid? 1, 2, 3. So what was this acid? What's a 3-carbon carboxylic acid? Propionic acid, right? But because it's an ester, we're going to take the ic acid and change it to 8. So what's the first part of our name? And by that I mean actually the last part of our name, the most important part that tells you it's an ester. Propionate. They're starting with the first part here, but propionate, so we had that right, right? Need to erase my box.
Why do you have the odd when you say it?
Propanoate? I don't know. Because that's the easy way for me to get it to roll off the tongue. I don't know.
Right. I was really just spell checking the slide.
Gotcha. So that's the propionate part, and then what's the first part? What was the alcohol that we used to make this? Or perhaps to rephrase, which side, if that was the carboxylic acid side, then that means the other side was the alcohol side, right? So how many carbons were in the alcohol? 2, and what would we have called that alcohol? Just ethyl alcohol or ethanol, right? And so that makes it an ethyl propanoate. Propanoate. See, now I'm going to be all self-conscious and make sure that I'm not adding eyes all over the place. It's an important call, because if I'm saying it wrong. Why are esters important? It's not just aspirin. A lot of the fragrances, perfumes, the things that we get from flowers and flavors of fruit, these are due to esters. Small ones are volatile. They're soluble in water. If they're volatile and soluble in water, it means that we can perhaps react to them on our tongue. It means that we can most certainly smell them as they escape the fluids of the things that we are eating. Pears, propyl ethanoate. Bananas, pentyl ethanoate. Oranges, octyl ethanoate. Pineapples, apricots. You ever wonder where artificial flavoring comes from? Because the chemical molecules found in fruits that give it their characteristic taste, one of the, or I should say some of the largest components of their characteristic tastes, these are chemicals that it is not hard for us to synthesize. We can make something taste like a banana by adding pentyl ethanoate to it. And we can synthesize pentyl ethanoate by combining ethanoic acid and pentyl alcohol, or pentanol, in an acidic solution. Purify it, and add it to your cough medicine. Or add it to the flavoring that you're going to dump all over your big ball of shaved ice.
Esters are also really good for saving the nation of Israel in captivity.
Nice. Aren't they also good for pillars of salt, or was that somebody else?
No, that was Lot's wife.
Yes, but what was your name?
He had to ask.
If we're going to make references. What's that?
Whatever request.
Exactly. Well, Google, it's right there. You have it on your phones. All right, so let's talk about the hydrolysis of esters. Esterification was the process of taking a carboxylic acid and an alcohol combining them in the presence of a hydrogen ion, either in other words an acid catalyst, and heat, right? So what's hydrolysis? Hydrolysis is the breaking of water. So why are we breaking water? Well, when we made that ester, what did we make along with it? Water. Esterification is a condensation reaction. It makes water. Hydrolysis breaks water. To do what? Take our ester and go in the opposite direction to make a carboxylic acid and an alcohol. Because remember when we were first introduced to that concept with esterification, we had two arrows, right? It went both ways. Ethyl acetate, a solvent that we use in fingernail polish, plastics, and lacquers. How could we make it? How could you make ethyl acetate? Tell me. What would you combine to make ethyl acetate? What would you combine in what solution? The solution part should be easy, I just told you. You need an acid, catalyst, and heat, right? But what two molecules would you be combining to make ethyl acetate? A little bit louder.
Ethyl, acid and ethanol?
Ethanoic acid, yes.
Yes.
And ethanol. Yeah. 2-carbon ester right here, right? Which comes from a 2-carbon carbonic acid. Carboxylic acid, I should say. So, ethanoic acid. And then this is a 2-carbon addition. That's the alcohol, right? So that's just ethanol. How do I know that the right side is the alcohol side? Because they could have been drawn differently. Once again, where's the carbon with 3 oxygens bound to it? On the left side, that's the acid side. That's how you tell. Where's the highly oxidized carbon? Would be another way to ask that question, right? The carbon with the most oxygen bonds. Alright, so now let's talk about doing that reaction that we just mentioned, but in reverse. That's when we take esters, react them in water with an acid catalyst to produce the carboxylic acid and alcohol. The water that we have here is broken up. So this is methyl ethanoate. So without looking too terribly hard on the right, what's the acid part of that? We have the carbon with 3 oxygen attachments right there. That is a 2-carbon molecule, so it's going to create ethanoic acid, right? A 2-carbon carboxylic acid. And then we have a single carbon on the right side. That's the alcohol. So what's a methyl alcohol? Just methyl alcohol or methanol, right? It's exactly the thing we've been talking about. We're just going in the opposite direction now. Notice a pattern, apply it, use it in both directions. Now, we can also do this instead of in an acidic solution, which is what we needed to make the ester in the first place, right? We can also hydrolyze esters in a basic solution. That has a spiffy name called saponification. Base hydrolysis. Hydrolysis in a basic solution. Because in this case, we're not going to make the carboxylic acid and an alcohol. We're still doing the same thing though. Pretend that this sodium right here, for a moment, pretend that that sodium was a hydrogen. What would this be? What would we do? We would take the hydrogen and we'd add it to the ester part, right? To make ethanoic acid. Or more specifically, actually, we take the hydroxyl, put it right there. We take the hydrogen and add it to that to make methanol, right? So, How is it different here? Here we're still keeping our methanol. We're getting the OH here is going to our methyl group to make methanol, but now instead of recreating ethanoic acid, that sodium is going to be bound to the ion. So we get the sodium salt, sodium ethanoate. But that's still just the same thing as ethanoic acid, right? It's just ethanoic acid as an ion with its other ionic compound. Because remember, this is an ionic compound. So in water, are these two things really bound to each other in water?
No, it's associated.
Yeah, they're disassociated. Because it's a salt, right? But if we dried that out, we would have methanol and this salt as a crystal. I know, so many rules, so many names. But we already talked about how to name our carboxylic acid salt, right?
So ceanothus flowers were the first source of natural soap because they release saponin.
I don't know. I don't know.
Does that, would that be good for cleaning?
Sodium ethanoate?
Something that's been
Oh, saponified?
There you go, yes.
I don't think so, no. Although the base hydrolysis, yes. Like, and just another aspect of why basic solutions or basic compounds are used as cleaners, yes. Because that's the same reason why we sometimes use acid cleaners. It's the same reason why we use hot water instead of cold water to get something really clean. It's anything that will break down compounds that will make them more soluble in water so that they will leave the thing that they are staining and therefore leave it cleaner. So that might be where the name comes from, or where soap comes from, is from that name. I don't know. Bless you. All right, so are we good with carboxylic acids and esters? Do we think we got that? Got it down?
I get how to do it.
Maybe sort of? Sort of? We've at least discussed them for a while, right? In fact, we've discussed them long enough that it is now after 7, so let's stretch our legs a little bit. 10-minute break. Put the light on your way out, stretch your legs, get a drink, wake yourself up, take a shot of caffeine in the arm, don't leave that last one.
In the Bible, her name was Lot's wife. But in Jewish literature, she's referred to as Ada or Edith.
Oh, okay.
So, wow, brownie points for knowing.
Something was done at the festival.
Thank you. Yeah,
I looked it up before.
there's more than one.
But there's like a second
Yeah, it's
not that.
carboxylic.
What?
We're going to have to take the disambiguation.
I'll be back in a minute. Yeah.
Oh, right.
How to turn this into that.
Only seeing the one.
No, bro, he's playing. Oh, maybe I'm thinking.
A fast preserved on a pure.
I'll try to mess it.
There's a feast of
It's
Esther.
just like I'm doing the whole
There's a feast of Esther. A fast observed on pure and from dawn until dusk on pure and where a 3-day fast was over the Jewish people in its glory of purity.
Because if I
Common
did it, then I
misconception
drop
of this feast was accepted by the Jews for all countries.
and then I'd be Sunday, 10:20.
I'm
doing that, but I'm doing it, I always do it like Sunday
My weekends are
afternoon.
my only time off, so I just I'm like on the go. Because I'm stuck at home 24/7.
Well, yeah, so you leave.
Esther.
Yeah. But I'll message you if I do.
Okay.
Have a good night.
You too.
They had established for themselves and understands the matters of the face fast and with pride. I waited till the end of the slides. I mean, it took forever to get to throw that joke in there. It's observed by Jews and Judaism.
Is that?
I just found that kind of ironic. The Feast of Esther is observed by Jews and Judaism, as opposed to the Jews in the Aztec.
As opposed to the Jewish people that are Christian, or the Jewish people that are Muslim, or the Jewish people that are Hindi. That's the thing. Judaism is both a ethnic group
Right.
and also a religious observation. So it sounds redundant, yes, but
One of my favorite little motivational poster is one of the guys in the can't remember the name of the group, but in full Hasidic dress, in like one of the kung fu poses, you know, kind of down flat,
yeah.
and it's not judo, it's oh man, okay, I'll have to find it. Oh, it's jiu-jitsu.
Oh. Jiu-jitsu?
Uh-huh.
I see. Got it. Cue play on words.
Was it Anastasia? There you go.
Oh, I see.
They will. We were doing an interesting dinner theater play on Passover as it relates to the Last Supper. And I found that if you go to like Michael's or Hobby Lobby, you get the doll hair curls. They make perfect
Oh, yeah.
payouts.
Yeah.
Very, very convincing. He's working out with your daughter.
Yeah. I'm trying to get her to come home, so
Where's she living now?
Virginia. Who hasn't she already? Is one of the questions.
Is she a free spirit?
Yeah, a little bit. She tends to kind of go and lose boyfriend all over the place. In the last 2 years, she's lived in Texas, Florida, Virginia, and Michigan.
You sure she's not on the land?
I start down there somewhere.
She'll bring home. Are you looking for a little boy or a little girl?
I just have this feeling she'll have a girl.
Well, you have at least a 50% chance of
Yeah, I
being
know,
right.
right? Well, I told my other daughter, I said, watch, you're gonna have a boy, and she did. But I only told her that because her little brother, who's like 15 years younger than her, you know, drives her crazy. And she's like, you just drive. I said, watch, you're gonna curse yourself and have a boy.
Yep.
And she had a boy, and he's ornery.
Well, I mean, it's like 51 point something more percent of the population is female.
I don't know what they got us beat, I just know that.
Of course, the reason for that is not necessarily because of birth rates as much as because men tend to remove ourselves from the population at a higher proportion than females.
Well, and we medically live longer, or shorter as well.
Yeah. It's just the
Is that world population you're considering?
world, I don't, yeah,